All right. Hey, everybody. Sorry that class got canceled today. We were kind of in limbo there this morning about whether it would or wouldn't. But as it turns out, class did get canceled. So I wanted to take an opportunity to finish out these lecture notes that we started on Monday over the series solution method. We got a little bit of the way into this. Let me kind of quickly go over what we talked about. First thing is classifying differential equations based on what are called singular points. Singular points, if you recall, are values of, in this case, x is the independent variable. So values of x that cause this thing to vanish. And depending on how bad it is, in other words, how easy it is to get rid of the singularity, they can be classified as either regular or irregular singular points. We went on to do this example together where we were looking at the singular points of this equation. So we had to get a leading coefficient of 1 dividing through here. And we found that x equal to 0 and x equal to 2 are the values of x that cause this term to disappear. And so we had to test each one of them. It turns out that 0 is a regular singular point and 2 is an irregular singular point. All other points, for example, x equal to 3, x equal to -4, all other values of x except 0 and 2 would be classified as ordinary points for this differential equation. And the reason that this topic turned out to be important is you're going to, in this lesson, solve differential equations by assuming the solutions are power series, plugging the power series into the differential equation and determining the coefficients. We had started to get into an example last time. This was that example. Turns out that the point that you need to be interested in is 0. So you're starting at x equal to 0. So we would be centering our power series at x equal to 0. So this is a power series centered at 0 form. And it turns out that x equal to 0 is fine. You can see here that only x equal to -1 is potentially a worrisome point. So we're staying away from any singular points. So x equal to 0 is an ordinary point. We're further looking at the equation in this form to check out what this function is. We'll talk more about that today. Whatever the power series representation of this term is going to dictate the radius of convergence of our solution. So we'll have more to say about that after we get some examples under our belt. So just recalling what we did last time, we assumed that the solution was of this form. So let me remind you what that form is. We're basically dealing with an infinite polynomial here, right? So our solution is of this form, and we're simply taking this and we're plugging it in for wherever y is in the problem. You want to keep it in series form rather than try to put it in as a polynomial. But as I discussed in class last time, when you take derivatives of polynomials, you can take the derivative inside the summation like we did here. So the derivative of x to the n is in x to the n minus 1. But the price you pay for that is, remember, you lose that 0 term. Since it's constant, the derivative of it makes it disappear. So your sum no longer starts at 0, your sum starts at 1. And I believe this brings us all the way up to current. This is kind of where we left off last time. So I want to pick up the problem from here. So I'm going to copy this down onto the next slide here. But I'm going to go ahead and distribute the 1 and the x here. So picking up from that last piece, we have the sum, n goes from 1 to infinity, of n a n x to the n minus 1. Plus, if we multiply x by this, we can bring the x inside the sum because the sum's with respect to n. So you bring the x inside, you end up getting x to the n there. So this would be the sum. N goes from 1 to infinity, n a n x to the n. And then the third piece here is this term, which I'll write just as is shown. Okay, so there are many different ways that we could proceed from here. Depending on books you read, authors will give different recommendations on how to go about this process. My recommendation is pretty simple. We're not going to be able to combine all of this into one sum unless all the powers of x are the same. So what I want to do is focus on this n minus 1 power right here. It does not match the other two. So what I would like to do is I would like to add 1 to that power. Now this is called reindexing a sum. So the index of the sum is here. So when I talk about reindex, I'm talking about changing the starting values, well, technically all the values of your sum. I want to make this x to the n. So if I do that, then I've got to replace n with n plus 1. In other words, I've got to add 1 to the n that's there. That way n plus 1 minus 1 cancels out. But I can't do that without changing the problem. So the way we do it is if I update n in one place, I've got to update n in every place that it occurs inside the sum. So what I've basically done is I've taken the term of my sum and upped it by 1. I've moved 1 term forward in the sequence. Well, I can't do that because it's technically not the same sum if all the pieces are moved 1 term forward. So I've got to start the sum 1 term earlier to offset that. So if I increase it by 1 here, then the n that's here is also n plus 1 equals 1. But that ends up meaning that n is 0 there instead. So the easy way to think about it is you add 1 to the variable, the summation variable inside the sum. But then if you add 1 in here, you've got to subtract 1 from it out here. Okay. So this moves you forward by 1 term, then you go back 1 term. So that's called reindexing. It's a very common practice for doing series solution method. Our new sum then becomes the sum n goes from 0 to infinity, n plus 1 a to the n plus 1 x to the n. And then we've got all of the other terms. Now, here's another place where things can get tricky. I now have all of the powers the same. However, I do not have all of the starting points for the sum the same. This sum starts at 1, the other two start at 0. To make up for that, I have to start every sum at 1. If I'm going to combine all of these, I'm going to combine them into one sum that begins at 1. And if I do that, I'm going to pick up pieces from every single one of these. Like so. But I'm not done yet because I left off the 0 term here and the 0 term here. So when I write the sum, n goes from 1 to infinity of this plus this plus this, I get the exact terms that I have here, but I skipped over n equal to 0 here and n equal to 0 here. Let's put those in. So let's put the n equal to 0 terms right here. What were they? Well, if n is 0 here, you get a1 x to the 0, so you just get a1. So a1 is one of the terms. If n is equal to 0 here, you get a0 times p, so it'd be minus p a0. So that's the n equal to 0 terms. Okay, so what I want you to step back for a second and realize at this point is the thing on the left-hand side of the equation here is a polynomial, an infinite polynomial that has a constant term. This is the constant term of the polynomial. And then the very first n equal to 1 here is for x to the 1. This is the coefficient of x in the power series. Then you would have a coefficient of x squared, x cubed, and so on. But the point is, this is a polynomial on the left-hand side. Now, if x cannot be 0, which we're not wanting x to be 0. You can see if we go back and look at the problem, x is the independent variable. It can be anything, right? So x equal to 0 is fine, but I'm also allowing for other values of x possible. I need this to be a function of x in the end. So I can't zero this out by just assuming x equals 0, and that's the solution. So the only way to make a polynomial 0 for every value of x is if all of the coefficients of that polynomial are 0. So here's what we need at this point. We need all the coefficients of this polynomial to be 0. So what does that lead to? Well, you've got this coefficient here. So this is for n greater than or equal to 1. You get that coefficient there. I'm just going to write down what we have. I'll start with n equal to 0. N equal to 0 gives us A1 is P times A0. So you can see that from here. I need this term to be 0. So if I set A1 minus P A0 equal to 0, this is the result. So I'm going to do the same thing for n greater than or equal to 1. I'm going to take the coefficient here. So n plus 1, a to the n plus 1 plus n. And if you'll let me here, this is n minus p times an. You can see that they both have a factor of an there. I need this to be equal to 0. I'm going to solve for the larger term an plus 1 in terms of an. So when I subtract this over to the other side, I'm going to make it a p minus n to accommodate that. So I'm flipping the order there. And then I would divide by n plus 1. So this formula is valid for generating all of the other coefficients in the problem. So you get started with generating the coefficients by looking at this piece. But then by looking at this piece, you get started. The question is, what is A0? Well, if you think about it, our solution, remember, is a polynomial of the form y of x equal a0 plus a1x plus a2x squared plus so on. And we're figuring out what a0, a1, a2 are. What is y at 0? Well, y at 0 turns out to be a0. And for this problem, y at 0 is 1. So a0 is 1. So I know right here that a0 is 1 and a1 is p. I immediately know that. So I know how my series gets started. I know it's 1 plus p times x to get started. And that's just from right here. So I want to make sure that we understand what the names of these things are. This is called a recursion. So this is a recursive formula or recursive definition for determining the a sub n, the coefficients. Because the larger subscript term is 1 larger than this term, so n plus 1 is 1 larger than n, this is known as a one-step recursion. One-step recursions only need one value to get them started. So you only needed one initial condition to get the one-step recursion started, because once you knew what A0 was, one step, you get to A1, one step, you now can get to A2 and so on. Now, we're actually still pretty far from a solution here, believe it or not. There's more work to be done. So what else do we need to do at this point? Well, I'd like to be able to write down an answer. Like I could easily come in here and say, okay, A0 is 1, A1 is 2. So what would A2 be? Well, A2, so I'm looking at this formula here for n equal to 1. A2 would be p minus 1 over 1 plus 1 is 2 times A1. So that's P minus 1 over 2 times A1 is P. So I now have A2. So A2 is P times P minus 1 divided by 2. Okay, let's just keep going, see if we can recognize a pattern. A3, so this would be this formula when n is equal to 2. A3 would be P minus 2 over 3 times A2. A2 we just calculated, so this would be P minus 2. Well, let me write it this way. This would be P times P minus 1 times P minus 2 all over, well, I pick up a 2 from here and a 3 from here, so this is going to be 3 times 2, and I'll leave it like that for right now. Let's go one step further, and then I bet we can kind of sense a pattern forming. This would be P minus 3 over, so this is n equal to 3 in this formula, P minus 3 over 4 times A3, which would be P minus 1, P minus 2, P minus 3 over 4 times 3 times 2. And I'm going to go ahead and throw in the times 1 on the bottom here because it's going to help you see the pattern a little bit here. So as we kind of run this forward, the question that we want to ask here is, do you recognize the thing that you're looking at? So in other words, can I write down a formula for what the nth coefficient in general would be? Well, based on what we're seeing here, it looks pretty reasonable that it's going to be this. You're going to get this product of factors of P here, and it's going to stop at 1 less than the index, right? So the last number here, P minus, this would be n minus 1, right? So P minus n minus 1 over, well, the number on bottom is clearly a factorial. So this is the fourth term in the series, and it's the denominator term is 4 times 3 times 2 1. That's forming a clearly a factorial. So this will be n factorial in the bottom. Most people will write it this way. So you'll see it written this way in the literature most often. And this is obviously, this works actually starting with n equal to 0. So this is n equal to 0, 1, 2, and so on. This describes all of our coefficients, which means our answer, our solution, is the sum, n goes from 0 to infinity, of an x to the n, but I just wrote down a formula for the an in general. It turns out to be this. But here's the issue. If I want this to be somewhat satisfying at the end of this, I say, well, great, that's my answer, but do I recognize it? So the question you have to ask yourself is, do you recognize this? So do we know what function this represents? And the answer for a lot of you is probably no, and that's perfectly fine if you don't recognize this. One way I may help you recognize it a little bit more is this coefficient right here is a different form than what you may be used to. Turns out that you can easily make the case that this is p factorial over n factorial n minus p minus n factorial, which in mathematics is something called the binomial coefficient. So this is p choose n. So this sum here is actually the sum n goes from 0 to infinity of p choose n x to the n. So if you have any familiarity with binomial coefficients, what you're looking at here is the binomial series. Now, this is just a question of whether or not you know what the binomial series representation of a function is, well, this turns out to be the function 1 plus x to the p. So this is truly our answer. And I just want to make sure that we understand that you're not always going to get a happy ending like this. Sometimes the best we will be able to do on these problems is write down the first 5 or 6 terms of the series and cut it off there and use it as an approximation, because we don't really know what kind of function we're dealing with. Sometimes you'll be able to actually find the general term of the sum and write down a nice looking formula, but you won't know what function that power series represents. And then the best of all worlds is where you can write down a ridiculously simplified formula that looks great and you know what function it's represented by. And honestly, this is kind of a chicken or egg question. Does the power series come first and then the function, or does knowing the function lead to the power series, or vice versa? When it comes to differential equations, the power series almost always gets a name if it's useful. So we end up coming up with, and you're going to see an example of this in the next problem, we're going to come up with a power series that we don't recognize, but because it's pretty useful and it shows up a bunch, we're just going to give it a name. And so we're going to take a look at that here in this next example. So we're going to do basically the exact same procedure we did. Like our procedure is not going to change much at all from what we did here. So the method, the nice thing about this method is it doesn't really care what your differential equation looks like. It doesn't care if it's first order, second order, third order, whatever. It doesn't care if it's linear, non-linear. Well, non-linear can be tough, but it doesn't care what kind of differential equation you have. You can still use this technique to solve it. Now, in fact, you cannot use this technique for nonlinear. I don't know why I said that, but you can use it for linear with non-constant coefficients, which we have here. We've got this x here, which is kind of gumming up the works. This is a very special differential equation. It looks like it's separable, and it kind of is, but it would still be difficult to derive the solution that way. In fact, more difficult. So we're going to use series solutions to do this. It's going to result in something called an Aries function. And so I want to take a look at this in Maple with you, because I want you to see kind of what we're up against here. And then I want you to kind of understand the limitations of this method when it comes to like plugging stuff into Maple. All right, give me 1 second, bringing up the file. So you have access to this file in Canvas. It's called Series Solutions in Maple. So this is the file that we are about to look at, that we're looking at together. This is the differential equation that we're about to do by hand. In Maple, when you're dealing with problems like this, if you just try to directly use a DSolve to get the general solution, Maple knows that this equation is tied to this function. I'm pretty sure that's just hard-coded into Maple. It's just known that the solution to this is this. We're going to figure out for ourselves here in just a second what area AI and area BI are. Then we want to evaluate this series. So this is how in Maple you can get Maple to show you different terms of the sum. So for example, I don't know what the area AI function is. I would like to know what its power series looks like. Here are the first 3 terms of that power series. In fact, it goes out to order 4, which means that it cuts it off at x to the 4th. So big O of x to the fourth means that the other terms are x to the fourth or higher in this series. I did the same thing for the other solution, area BI gives us, once again, the first four terms of the series. There is a series option for desolve. So if you go into the desolve command and desolve this differential equation at starting points A and B, it'll show you kind of what the formula is for the first couple of terms. And what I want you to see here is the initial condition A only affects every other term. The initial condition B affects every other term. So this is going to be very different once we get into it by hand here in a second than the problem that we just finished. So here you can see a solution when A is 2 and B is 3. By default, the series option for desolve will give you up through big O to x to the sixth. You can change with the variable order. It's a global variable or an environment variable. So if you change order to be 10 and redo the sum or redo the desolve with the series option, you can get up through the 10th term. This is actually very efficient for Maple to solve things in this way because it's finding an approximation. It's not having to actually find the general solution to these. The general solutions are quite horrific when all the terms are kind of written out, as you'll see here in a little bit. This is what both of those functions look like when plotted. So, these are actual functions, just like sine of x is and cosine of x is. Sine of x and cosine x have power series representations, just like these two functions do. You can see I've given you another example down here to look at, but I encourage you to take a look at this Maple file in particular between now and this weekend as you kind of start to work on the homework here for module 4. All right. Well, trying to find where my thing went to. I might have to redo it here. Oops. All right, let me try to bring this back up real quick. All right, I got it to reconnect. So let's dive in and see if we can actually solve this one by hand and see kind of the difficulty that's involved here. We're going to start with the differential equation, y double prime minus xy equals 0. Remember, just like on the last problem, originally we had it in this form, but I divided through. Don't use this form. Try to keep things without a quotient or a fraction as much as you can. Here, we're lucky there's not too much going on that's difficult here. There are no singular points for this equation, so any point that we would choose to start it makes sense. So I'm just simply thinking of this problem as being this. Now, it is a second order differential equation, so we know from prior experience, I'm going to need two initial conditions in order to be able to do this. So I'm going to call those two initial conditions A and B. Keep in mind, by the way, that y of x here, if it's a naught plus a1x plus a2x squared, and so on, then y of 0 is going to be a naught, and y prime at 0 is going to be a1. Okay, so this term is the initial condition at 0. This term is the derivative at 0 for our series. That'll come in handy here in just a little bit. So we're going to guess that our solution is the sum n goes from 0 to infinity of a n x to the n. There's no reason to center this at a point other than 0 because 0 is an ordinary point. So if I was going to list initial conditions for this, I'd want them to be listed at 0 anyway. And so this is our guess that the solution ends up looking like this. All right, if I plug it in, I'm going to take two derivatives of this thing. Now let's see if we can do this without having multiple steps, kind of see if we can do this a little bit more efficiently. We're going to take two derivatives of this. So I'm going to differentiate inside the sum twice. So what would that look like? That would be the sum. One derivative will bring down an n. The next derivative will bring down an n minus 1. You'll have a to the n, x to the n minus 2. So if I take two derivatives of x to the n, this is what I would have. Now, if you take two derivatives, a naught goes away, a1 will also go away, you'd be left with a2. So this sum is going to start at 2. You've taken two derivatives, so you've knocked off the first two terms of this. So we're going to be starting there at n equal to 2. And then it's going to be minus x times y. Just copy down what our solution for y is there. So equals 0. All right, so same song, different verse. Here is the first example that we were looking at. A couple different ways to go about it. Once again, I like to get x to the same power in both of them. So I would recommend the next step for you should be to bring this x in. If you do that, this is now an x to the n plus 1 power. And you know, here's what's potentially interesting about this one as compared to the last one. I mean, there's a lot of things that are interesting about it compared to the last one. The most interesting thing to me is that there's a difference of 3 between these powers. And that's not the easiest difference to overcome. So here's what I'm going to do. I'm going to get them both to be x to the n, because I like dealing with x to the n better. So what would we do on this one? I need to add 2 to this power. So I'm going to add 2 to all the n terms here. Don't forget to add it to the general term as well. But I have to, if I'm adding 2 here, I have to subtract 2 here. So this sum would start at 0, and it would be n plus 2, n plus 1, a n plus 2, x to the n. And this one starts at n plus 1. So I actually have to subtract 1 from these terms, which will add 1 to the sum. So the sum here starts at 1, and we are subtracting 1 from these terms. All right, so we're in decent shape here. So kind of looking on to the next page here. This would be the sum. N goes from 1 to infinity, and I'm going to capture all of it here. I know that I have to start at least at n equal to 1, because this one doesn't have an n equal to 0. So I'm going to end up pulling out the n equal to 0 term here in just a second. But this will be n plus 2, n plus 1, an plus 2, minus an minus 1, all to the xn. Then we're going to have the n equal to 0 term here, and all of this will equal 0. So what is the n equal to 0 term? Well, if you plug in n equal to 0, you get 2 times 1, a2 x to the 0, which is 1. So I guess I didn't need that much room. So this is the n equal to 0 term, and this whole thing is 0. So just like before, we set each of these pieces equal to 0. So this is for n greater than or equal to 1. I'm going to set for n equal to 0, my coefficients are 2a2 equals 0. So I know a2 is 0. And for n equal to 1, or n greater than or equal to 1, we have just taking this and writing it down as is, then we'll simplify it. We have this. So I can solve for the larger of the two subscripted terms. You always want to solve for the larger one. So n plus 2 is a higher subscript than n minus 1. I'm going to solve for this term. This would end up giving me a n plus 2 is equal to a n minus 1, but then I'm going to go in and divide by n plus 2, n plus 1 here. And this formula is valid once again for n greater than or equal to 1. So we've got our recursive definition. By the way, this is one of the goals for doing this on a test is you'd be able to give me the recursive definition. You'd be able to give me any of the constant terms or starting values here. So let's kind of figure out what's going to happen here, because this is sort of interesting. If you look at what we have, remember I said that a naught, y at 0 equal a naught's going to be a, and a1 is going to be b, okay? So in addition to this, we know that a naught is a, and a1 is b. So we actually end up getting 3 initial terms here, which is needed because if you look at this recursion, this is a 3-step recursion. The difference between the highest subscripted term and the lowest subscripted term is 3. The difference between n plus 2 and n minus 1 is 3. So I actually need 3 initial values to get started on this problem. So we've got those terms. How would I calculate A3? Well, A3 would be this formula when n is 1. You can see that A3, when n is 1, you get A0, which is A. So you get A over n plus 2, n plus 1 here. Okay. Sorry, n is 1. So it'd be A over 3 times 2. Then you look at, say, A4. What would A4 be? Well, A4 would be n equal to 2, A1. A1 is B. So n equal to 2, you get B over, in this case, it would be n equal to 2, you get 4 times 3 there. Let's keep going with this a little bit. A5 would be, so here's where it gets interesting. If you look at A5, that's when n is 3, but that gives you an A2 here, right? So, but A2 is 0. So when n is 3, this term becomes 0. So you get 0 for that. But that's interesting because that means all future ones are going to 0 out. If A2 is 0, then A5 will be 0, A8 will be 0, A11 will be 0. All of those will be 0. So we've eliminated a third of all the coefficients now. They can't exist. So what we really need to do is we really need to concentrate on a pattern for the A terms separate from a pattern for the B terms. So let's continue to write those out and see if we can indeed come up with that pattern. So let me write out the terms for A3. So A3 is A over, and it's going to be 3 times 2 times 1. You can see here that A6 is going to be A3 over 5 times 6, which means it's going to be A over 6 times 5 times 3 times 2 times 1. And I'll do one more term there. If you looked at A9, A9 would be A6 over 8 times 9, which will turn out to be A over, let's see here, I get 9 times 8 times 6 times 5 times 3 times 2. You get this interesting skip of some of these terms in here, which means this isn't a straight factorial. So there's some of the values for multiples of 3. So the coefficients that are multiples of 3 will depend on A. What about the coefficients that are one more than multiples of 3? So like A4 we wrote down earlier, A4 is B over 4 times 3. So A7 would be the next one in that sequence. A7 would be A4 over 7 times 6. But since we already know A4, this would be B over 7 times 6 times 4 times 3. And then finally, A10 would be A7 over 10 times 9, or B over 10 times 9 times 7 times 6 times 4 times 3. So there is enough for a pattern here, because we kind of see what this thing is going to do, but it's just a question of like, how do we write this thing down? So here's what I recommend. Y of x is going to be equal to, all of these terms are multiplied by A. So I'm going to start with these multiples of 3 coefficients. They're all multiplied by an A, so I'm going to bring A out of the entire thing there and just focus on what the sum looks like. So the sum here starts at what value? Well, it technically goes all the way back to A0 and A1. So the first term here, A0 is A, and A1 is B. So those are a part of the sequence of multiples of 3. Here it's one more than a multiple of 3. So if I'm looking at this, this one starts at n equal to 0. The very first term in this, I don't have a general form, so I've got to do the best I can. It appears to be 1 over, here's how I would personally write it. We get, you can see here, I'm looking at the stuff that looks like this. We get 2 times 3, then it skips, and you get 5 times 6, then it skips, dot, dot, dot. What would the last 2 terms be? Well, it's whatever the subscript is, right? So whatever this is, whatever this is, right? The highest number matches the subscript. So here the subscript, I'm trying to write down what A sub n would look like, right? So this is, I'm trying to write down what A sub n would look like, but that's, that's kind of difficult to do because I really want to make multiples of the 3. So I really want to write down what A3n looks like, right? So what do all the multiples of 3 look like? Well, the highest, if this is A3n, the highest term here would be 3n. So you would have 3n minus 1 times 3n. So you can clearly see that from these examples here, okay? All right. Just double check that this is written down correctly. Yeah, this looks good. So this is going to be times x to the 3n. So the coefficient 3n goes with the power 3n, right? So an, this is the coefficient of x to the 9th power, would be this value here. All right, I can do a similar thing for the terms that are multiplied by b, which are all the multiples of 3 plus 1, right? So 4, 7, 10, and so on. These also, I'm going to start at 0, but these are one more than a multiple of 3. So what I'm describing here are all the terms of the form a 3n plus 1. And they belong to the power x to the 3n plus 1. And the general form that they take, we would write down as, just kind of looking back through our examples here, the smallest we have is 3 times 4, then it goes to 6 times 7, then it repeats, and the highest power that you have here is equal to the subscript here. So once again, it makes sense to call this, and you have to be careful here. I need to end with a 3n plus 1, right? Because it's got to match the subscript, right? The highest power or the highest factor in the bottom has to match the subscript here. So in general, this would be 3n 3n plus 1 for that term. So we've written down the answer. I don't know how satisfying this answer is because we didn't have a great closed form expression for the coefficients, but this is our answer. So this is the final answer, if you will, or the general answer to this problem. But I want to take it one step further because mathematicians have given these things names. This one is the Airy function. So this is Airy AI of x. And the one that's multiplied by b is Airy BI of x. And you can check those out in the Maple file, but this is these are the names given to these power series. So if it's a series that you recognize, then you would do it all the way out. But if it's a series you don't recognize, then literally all I would ask you to do is write out the first couple of terms of the series. And so you're going to practice that on your quiz, your skills quiz, or not skills quiz, on your homework for this. You're going to practice a couple of these series problems. All right, so kind of want to sum up some of our efforts here with what's called the ordinary point theorem. Like, when can we do this method? How often does it work? Why does it work? So this theorem kind of summarizes a bunch of that. So suppose that you have a differential equation of this form. We're looking at second order problems almost exclusively for this topic this semester. So this is the second order ordinary point theorem, but there exists a similar theorem for third order and so on. Suppose that I know my functions p of x, q of x, and g of x all have power series expansions at the point A. In other words, I can solve for representations of these functions at A, centered at A. Well, that means that I can express a solution to this differential equation, which is also centered at A. And I know that the radius of convergence of this series, in other words, the interval of existence, if you will, in terms of how good of a job this does approximating the answer, I know that it's a good approximation. In other words, if I use more terms of the series, it gets closer and closer to the actual answer, so long as I'm within the minimum of the radius of convergence of those three terms. So whatever these functions are, the minimum of their radius of convergence is also the minimum of the radius of convergence of my answer. That may not be super satisfying, so let's look at an example and then remind you of how we compute radiuses of convergence. We're going to have to look at the radius convergence of p of x and q of x. So how did you find radiuses of convergence in Calculus 2? Well, you could compute the power series, which is what we've done today with the series solution method, then use ratio tests. So like going back up to this guy, here's the general term. You could do ratio test on this, right? So this is A3n. So ratio test is you would do a to the 3n plus 3 over a to the 3n. You would take the limit as n goes to infinity of that, and you would look at whether the absolute value or whether the value of that is less than 1 or not to determine convergence. I would encourage you to go back and look at that stuff from Cal 2. But there is an easier way, so long as the functions here are rational functions. Now, rational functions mean that the function can be written in the form q of x over p of x, where both q of x and p of x are polynomials. Turns out that most of our ODEs we actually care about this for have that property, that these terms here will be a polynomial over a polynomial, polynomial over a polynomial. It's kind of like this example we did last time here, where we're looking for ordinary points and singular points, polynomial over a polynomial, polynomial over a polynomial. And for rational functions of that type, finding the radius of convergence, there's a neat trick that you don't have to do ratio test. These functions will always have a convergent power series at an ordinary point, so a point where it doesn't vanish, if we've completely reduced the rational function. So any terms that are in both the numerator and denominator, you have to cancel out. And you look at the distance from your point that you want to center at. So this is your center around point. This would also be where your initial conditions are. You look at the point that you want to center your solution at, and you look at the nearest zero of the denominator. Now, this also includes the complex plane. So let me show you an example. Suppose we wanted to solve this differential equation. What would be the radius of convergence of our solution? Suppose we wanted to center it at x equal to 0 and center it at x equal to 4. Now, there are no values of x that make this term disappear. So there are no singular points here. Clearly, plus and minus 3i make it disappear, but we don't really care about those values. If I wrote this equation in standard form, it would look like this. And so here's what I'm trying to do. So case 1, suppose y of x is the sum and goes from 0 to infinity a n x to the n. In other words, I'm choosing x not equal to 0 to be my center point or ordinary point. Versus case 2, which is suppose that the solution is centered at a power series centered at 4. So that would be x minus 4 to the n. So here x naught is 4. I want to list over here what are the radius of convergence for each of these examples. In other words, what interval, how far can I go, right? Radius of convergence tells you how far can I go from x naught until y of x is a bad approximation, right? So that's what the radius of convergence is essentially telling you here. So what this right here is what I'm using. What this tells me is I can go from my center point to the nearest 0 of the denominator of these terms. So I look here and the denominator is x squared plus 9 for both of these, which factors into x plus 3i, x minus 3i. And yes, if you look back at that previous slide, I have to incorporate any complex zeros as well. Well, let me give myself a little bit of room, so I want to draw a picture here. So we'll start with, we're in the complex plane because these zeros are complex. So this is the real axis. This is the imaginary axis. Our first center point is at 0. So x naught equals 0. Now, where are our roots? Well, the roots of the denominator here are at 3i and minus 3i. So the question you have to ask yourself is, how far is the center point for case 1 away from the roots of the denominator for these two functions? Well, they're 3 away, right? There's a distance of 3 here. So I know I would be able to travel a distance of 3 on either side of this point. So my radius of convergence is 3, absolute value of x less than 3. The radius technically is 3, but the interval of convergence would be -3 to 3. Now, I would have to check and see if I can include the endpoints or not. This only tells me open interval, how far I can go. I'd have to plug in x equal to 3 into this series and figure out if it includes it or not. Once again, go back and look at some stuff from Cal 2 to remind you of what is involved in that process. What about for the case where I'm starting at 4? Well, if I have 4, so x not equal to 4 here is where I'm trying to center my series. How far away from the nearest root am I? Well, the roots are here and here. Question is, what is this distance? Well, this, if I'm not mistaken, is a 3, 4, 5 triangle. So this distance is 5. This center point is 5 away from either root. And you want to take the minimum distance away. So if one of them, if it was 5 away from one and 4 from the other, you would use 4. So the radius of convergence here turns out to be 5. We can go, but be careful here. It's not absolute value of x less than 5. We're centered at 4, so it's absolute value of x minus 4 less than 5. So the actual interval is from 4, you can go 5 in either direction. So if you go to the right, you end up at 9, but if you start at 4 and go to the left, you end up at -1. So that's actually our radius of convergence for a solution using this as a power series in this case. There's a lot that I unloaded on you here. If you are struggling a little bit, this is definitely a topic you're going to need to read more about, because we just have to kind of move on to the next topic. Luckily, this is something that doesn't really come into play until late in the semester, but I wanted to do it now since we're talking about some stuff from ODE that isn't covered in the ODE course that's important in the PDE course. Remember, there is some material on this in Appendix A of the textbook. I actually have some videos for this because I used to teach this topic in ODE, so make sure you check out those. All right, I will see you in class on Friday, hopefully, and we'll be taking a look at what are called eigenvalue problems. All right, have a good day.